Thank you all for coming here, and I'm going to be doing from the title you might have guessed it, but a little bit of a controversial talk. Now actors are becoming quite popular, and I'm going to say quite a few things about them. So I didn't anticipate that this would be during the lunch break, so please refrain from throwing food at me at least until the end of the talk, until you hear the whole story. My name is Jaksa Vuckovic, and I put my title there not really to brag about it, but just to reassure you that what I'm saying is actually backed up by several years of research in distributed systems and collaboration with with some of the greatest minds in the distributed systems community. So, what's the actor model? You probably have an idea about it since you came to this talk, but actually you've probably heard about the actor model from frameworks such as, or languages, such as Erlang, Akka, or maybe Quasar. Well, actually the actor model was invented in '77 in a paper called Laws for Communicating Parallel Processes, written by Carl Hewitt and Henry Baker. Or, if you actually take a better look, it was written in the Semantics for Communicating Parallel Processes by Irene Grief. That was her PhD thesis, and she was a student of Carl Hewitt, actually 2 years before that. Now, you can go and read the original paper, which has a lot of mathematical abstractions. But actually, it's quite simple. It's not as scary as it may look. But just to summarize it, the actor model is something that where each actor has a kind of a message queue. Upon receiving a message, the actor will change its state, which, in other words, we can say it will define how it will react to the following messages. It may spawn other actors, and it can send messages to other actors. One important property of actors is that they are reactive. This means that they will only react to messages they receive. They will be processing these messages one by one, and while processing a message, they will not block. Now, this has some consequences. This has actually quite important consequences from a theoretical point of view. But it has also some consequences on the frameworks that we've been mentioning. In fact, both Erlang and Quasar are not reactive. They actually have a blocking receive primitive, which actually makes them implementation of the communicating sequential processes model. And actually, Erlang was set out to be an implementation of CSP, not actors. This is a common misunderstanding. Now, Akka is the only one which gets close to the actor model, with a few exceptions. These exceptions are just minor, but in spirit, it is the actor model. Now, if you know the actor model, you've also heard about all the benefits of the actor model. So, easy to use, there are no deadlocks, they're elegant, they're completely fault tolerant, and they provide this massive parallelization. Now, actually, all of these are myths of the actor model. So what's really the truth is that they're not that easy to use. So let's take, for example, the philosopher's dinner problem. You probably all solved it during your uni days, and you know what the problems are. Now, here on the left, you don't really, maybe you can see the code, but this is an implementation, a solution of the philosopher's dinner with the traditional threads and locks model. So we have multiple threads, we have locks, and it's just a few lines of code. I actually wrote this in Scala just to be fair for the comparison. This one is a solution written using actors and Akka. Actually, this is a little bit more. And actually, this is shorter, half as short as the shortest solution I could find on the internet. So they're not that easy to use. Can they have deadlocks? Really? Is it possible to write a concurrent system without deadlocks? Well, actually, here is a deadlock of the previous example. The previous implementation had one small omission, which actually forces it into a deadlock. So yes, actor models can have deadlocks. Are they elegant? Now, there was a, I don't know how many of you are familiar with Dijkstra's paper about the go-to statement, when he complained that the go-to statements was very disruptive to programmers. And actually, if you read the paper, it's a very useful paper because you can read the paper and substitute the word go-to with any construct of any modern programming language and verify whether that programming language is actually making a step forward or step back. And if you look at the points that Dijkstra made, basically the points are the distance between the program representation on the screen and what happens during the execution. And basically, while we read the program, Dijkstra says we should be reading the story of the program, what is happening, which is very difficult if you have a go-to statement, because you keep jumping around and your trail of logic is very different from the sequence of instructions that you see on the screen. Actually, the same thing goes for actors. If you think about it, it's precisely what's happening when you program with actors, because you're sending messages back and forth and codes gets executed all over the place, and there is no actual indication, visual indication of what goes after what. And this makes debugging really hard when you're dealing with actors. Now, fault tolerance actually was kind of the specifics of my PhD thesis. So basically, there is in the fault tolerance research community, there's a quite good understanding of what fault tolerance means. And for example, all these frameworks for message semantics, they have at most once delivery, which is the worst case you can get. You send your message and at most it will be delivered once. It can happen that you lose your message. Crashes, well, for example, akka by default does only crash detection. If you're using akka clustering, you get also restarting of your crashed actors, but that's not recovery. Recovery is something you have to do once your actor is restarted. And for stateless actor, this is trivial, but if you have a stateful actor, then that gets a little bit more complicated, especially in a distributed systems scenario where you have global consistency. So really, what these frameworks provides us is not very different from exceptions, because they actually give us a way to detect crashes, but they do not handle fault tolerance transparently. There are other models that do that. And another thing that's quite goes against what everything fault tolerance is about is the supervisor hierarchy, where actors are usually organized in this hierarchy when there is a single actor at the root of it. And this is a single point of failure, and this is really bad design pattern, anti-pattern. About parallelization, well, this is also kind of a itchy topic, because we have the akka benchmarks which show really significant performance improvements to threads. But actually, you know, there are lies, there are big lies, and there are benchmarks. And there's quite a bit of difference between scalability and performance. And actually, those benchmarks are not showing scalability, they're showing performance. And performance is much easier to reach if you have a lot of small objects and can take advantage of cache locality. I mean, anyone who's done game programming knows that. It's like you can get 50 times improvement if you just organize your objects in contiguous spaces of memory. If you've done any really serious parallel systems programming, then you can have a look at GPGPU. Now, GPGPU can spawn thousands of threads in a single instruction. Now, that's parallelism. There's a quite a bit of difference between concurrency and parallelism in terms of goals, in terms of which qualities are desired, and actors have to deal more with concurrency, not with parallelism. And concurrency is on the same level as threads and locks. And actors, to be parallel, are really missing a primitive broadcast, something that will allow us to scale in a much faster way. Also, there are common anti-patterns, because if you have an actor-based system and you have an actor singleton, it's like if you introduce a global lock into your system. So you will still end up having bottlenecks. And there is danger in terms of performance doing a system with actors if you do these kinds of mistakes. So what's really the truth about the actor models? Are they easy to use? Well, they're mostly for experts. There are no deadlocks? Well, try implementing the dining philosophers and you'll see. They're elegant as a go-to statement. You have to build your own fault tolerance. They don't provide it for you. And they're not really about high parallelization. Now, if you really want to know why actors are awesome, I suggest you to come to our workshop tomorrow at 1:20 in the workshops room upstairs. So that's it. Now you can throw your food at me. Any questions? Any remarks? Okay, thank you very much.